Welcome to Solideo Gloria Physical Chemistry. This is the fourth lecture in quantum theory. And so we are going to solve Schrodinger equation of the rigid rotor, which is the associated Legendre differential equation. First, we will see about rigid rotor, which has two bodies. M1 and M2 with the mass, and there is a center of mass, and then the distance from the center of mass R1 and R2. And basically this is the relationship M1 R1 equals M2 R2, because that's the center of matter, center of mass, that's the center of mass. And then the total distance from M1 and M2 is R1 plus R2, of course, and then R1 and R2 is given this way, and the width and that defines the moment of inertia, which is I equals to M1 R1 plus square plus M2 R2 square. And then we introduce the reduced mass, which is given here, and the reduced mass, with the reduced mass, the moment of inertia is mu R2 R square. Okay, so we have done with this. And then the velocity of the two bodies on M1 and M2, V1 and V2, and which is in terms of the rotational frequency, 2 pi R1 rotational frequency, and then 2 pi, the frequency is the angular velocity, so R1 omega, and also V2 is R2. Actually, you know, this V and Ni kind of can look identical in this font set, but anyhow, that's Ni and that's V, and V2 is R2 omega. Now, the angular momentum is defined in terms of moment of inertia with the angular velocity, which is L equals I omega. Okay. Now, Hamiltonian, which is the total energy, is the sum of kinetic energy and the potential energy. In this case, this is rigid rotor. Because of this is rigid, and then we expect that the distance from M1 and M2, the length R is fixed, so R is constant. Then the kind of potential relative position, based on the relative position, is fixed, so that's constant, and because of that the potential energy is 0. And also R is constant, the diminutive R is also 0, so have this in mind. So R is 0, have this in mind, we'll derive the kinetic energy term. So kinetic energy is 1/2 of mv1 square plus 1/2 of m2 v2 square, and this V is given here. In terms of that, R1, V1 is R1 omega, V2 is R2 omega. So now mv1 square is m R1 square omega square, V2 square is R2 square omega square. So we have this relationship, and then m1 R1 square plus m2 R2 square is what? The moment of inertia. So moment of inertia comes here. So kinetic energy itself is 1/2 of I omega square. Okay, and then if you divided, if you multiply with I and divide by another I, then what you have is I square omega square, which is L square. So kinetic energy is given in terms of momentum square. So kinetic energy is momentum square over 2I. Anyhow, so total energy, which is only kinetic energy, is given here. But you see, now we can introduce normal Laplacian kinetic energy operator. You remember that, which is minus h bar square over 2m d square dx square, like that. So in 3 dimension, we use the Laplacian operator in the position of the kinetic energy operator, which is round scale round x square plus round scale round y square plus round scale round z square. But here we are dealing with r, theta, phi, so-called polar coordinate. So we have the polar coordinate, we have the Laplacian operator in polar coordinate in this way. And I urge my student to kind of have this in mind, I mean, memorize it, but there is a way to kind of draw from Cartesian to convert Cartesian to polar coordinate. So anyhow, this is the Laplacian operator. Our kinetic energy term is given here, minus h bar square over 2 mu del square. And we read this as del square. So this is the Hamiltonian we are going to solve, we are going to use in the Schrodinger equation. Okay, so Schrodinger equation, well actually this is just a repeat of the previous slide. And then R is constant, there is no, the potential energy is 0, and then dr equals 0. And so we have only kinetic energy term in the Hamiltonian, which is this. And then we are going to solve this Schrodinger equation. And the solution for the Schrodinger equation is denoted here as y. Well, actually, this is epsilon, theta phi. And then this y, theta phi, we call spherical harmonics. This is the name for this function. Then that is the solution of this Schrodinger equation for the rigid rotor. So h is given here, minus h bar square over 2 mu. This, the blue part, is the Laplacian operator. Now, dr equals 0, so we don't need this r part here. So we remove this r part, then we with only theta and phi part, theta phi part. So this is the Hamiltonian. Now we introduce the moment of inertia into this. Well, actually here, how it works is that there are all terms have r square. So r square mu r square is I. So minus h bar square of 2i, and then only the theta and phi part of the Laplacian operator. Okay, and also r is the constant here. So h, the total energy operator, actually that is the kinetic energy operator, which is, we have seen this before, L square over 2i. Now L operator, L square operator is just this one, minus h bar square, and this part, meaning is here, minus h bar square, and then angular part of the Laplacian operator. So h psi e psi, in this case we're using spherical harmonics, so h y e y, or if you know what this letter in Greek, that is h epsilon equal y epsilon. Oh, that's epsilon, yeah. Okay, so minus h bar square over 2i, 1 over sine theta round theta, sine theta round theta, plus 1 over sine square theta round square round phi square, and spherical harmonic, and then energy spherical harmonic. This is the Schrodinger equation for the rigid rotor in terms of theta and phi. Okay, so I repeated here. In order to solve this, we are going to go step by step, and eventually we are, firstly we separate the variable, and then solve separately. So theta phi part first, and then we'll work on the theta part. So to have this in kind of succinct form, we just multiply with sine square theta, then let 2ie over h bar square as beta, because we multiply with 2i over h bar square both sides, then get 2i e over h bar square, and that we substitute or replace with beta. Then if you find beta later on, the energy is given by 2 beta h bar square over 2I. That's the energy. You remember that later on. Okay. So if we do that, we get sine theta round theta sine theta round y round theta plus round square y round p square. And then we have this beta, well, actually energy term in the same side, in the same side, which is sine, and also we multiply by sine square theta, beta sine square theta y equals 0. So this is the equation we are going to solve, and by doing so we separate the variables. So y of theta phi equals theta only function times phi only function. So if we do that, we plug into theta phi here, then phi part does not differentiated by round theta. Theta part does not differentiated by round phi. So it is considered to be a phi, in this phi is considered to be a constant here, and this theta is considered to be a constant here. So they are passed through the differential operator. Okay. Then what we do is that if divide both sides, actually divide by whole y theta phi, meaning theta times phi. Then the theta part was here, and then theta part is divided by theta and the phi. No, phi part was here because this is differentiation with respect to theta. So this theta phi, this phi was here, and then divide by theta pi, meaning is that you have 1 over this theta. Okay? So now that's what you have here. And then of course you divide by theta phi whole y, then you have this term, and then for this you have this term. So basically you have done the differentiation of the separated function. Okay, so now this term and this term, these two terms are only in theta, and this term is only in phi. So you separate it over the equal sign. So this part is the theta part only. This is only in phi only. Only in phi, only in theta. So two part, the independent variable is different. Then what we can expect to be those two are equal, which is a constant. So we adopt a constant m square, which will make later on the derivation is kind of simple form. Okay? So this is only theta only function. This is only this is phi only function. So we let them equal to m square. So with this m equal to m square, this part is equal to m square. That part equals to minus m square. Okay? This and this. So this is theta only function. This is phi only function. So firstly, we will solve phi part. So which was that d square phi, d phi square equals minus m square phi. So we have this form. Then this is a linear equation. So d square plus m square equals 0 will give you a kind of form of the solution. So one of them is this. So phi m, phi equals a constant, and e to the m phi. Okay. So but you see that phi goes from 0 to 2 pi and goes on. Then every 2 pi of revolution, you will hit the same point, which means that there is a boundary condition, phi plus 2 pi equals phi or phi. Okay, and then this boundary condition will give you restrict your m value, which is because this equal am is cancelled, and then what you have here is im phi times I am 2 pi. Then this has im phi here, which is cancelled. So what you're left is that e to the plus minus, well, actually you can go this way or also the other way. 2 pi m equals 1. In order to be this correct, this met, you must have m equals 0, plus minus 1, or plus minus 2. Alright, so this, well, now the boundary condition, we have been seeing this several times in the particle in a box, and then particle in a box. Once there is a boundary condition, meaning is that the particle is restricted, or your system is restricted, quantization reveals. Okay, so you have the quantum number, and then we denote the function with the quantum number, phi m phi, like this. Okay, now what you have to do is now determine this constant. Actually, that is the normalization factor. So with respect to phi, the variable phi, your probability must be normalized, which means that if you integrate entire space, meaning here is the 0 to 2 pi, you shall have to have that integral equals to 1, which is the normalization. And then now you do that 0 to 2 pi, your function, star function. This is a complex function, this is the right form. And then what you have here is that if you have a complex of this is minus im phi, and regular one is im phi, then what you have is am square, and then that's just 1 here, and that's 2 pi for this integral. And so 2 pi times am square is 1, so am square is 1 over 2 pi, so am is 1 over square root of 2 pi. So you have determined the normalization constant, and this is your function. Okay, this is your function. Now you index it in a way with the quantum number m. So that quantum number phi m, so we denote it this way. Phi m phi equals to 1 over 2 square root 2 pi e to the im phi. M is equal to 0 plus minus 1 plus minus 2. So we have solved this part, and then we just solve another theta part only now. So we have done halfway through, but the other half is a little bit lengthy. Now, so this is the theta part. So theta part is, if I read it again, sine theta d d theta. Well, now this is the function of theta only, so we use d instead of round, and sine theta d theta, then plus beta sine square theta theta minus m square theta equals 0. Now you remember that the beta was that 2ie over h bar square, then your energy equals to beta h bar square over 2i. Okay, you remember that? And then in order to solve this, we are going to convert the variables, okay, to handle easily. Okay, so let x equals to cosine theta. Then of course, then your function theta of theta, we'll use different symbol for that, p of x. Now dx is minus sine theta d theta. See, and then you can do this in a way that 1 over theta equals minus sine theta 1 over d theta. I'm sorry, dx. Okay, you do this substitution. So you have sine theta, and then minus sine theta 1 over d dx. Okay, so basically what you have is minus sine square theta d dx. Now this part also you have minus sine square theta d dx. So minus minus plus. Okay, what you have is that sine square theta. Sine square theta is 1 minus cosine square theta, which is 1 minus x square. So 1 minus x square ddx, 1 minus x square ddx. And then you replace this theta with p. This part is just delta, okay, and sine square theta, which is 1 minus cosine square theta, which is 1 minus x square here. Then you just have replace theta with a p, and this is it. Okay? Now, this equation, see, for this equation, we just divide by 1 over theta square. So you have this, and this removed, and then theta minus m square over 1 minus x square p equals 0. So you have to solve. Now we are going to solve this equation, and then a kind of one thing we notice here is that 1 minus x square is in the denominator, meaning that there is a singular point, x equal plus minus 1. Okay, so this, in order to make this a regular function, we'll do this kind of transformation. So px, in this case, just the replacement of this independent variable. But px, now we transform into this form, 1 minus x squared to the m over 2's power and gx. Okay? Gx is a function of cosine theta, of course. Okay, x is the cosine theta in this case. Yeah. Right? So remember this, and then this, and then we'll go on. Okay, so see, I repeated here, and then you see this. This is the form of the differential equation equal 0. So we have to do differentiate, multiply, and differentiate, and this is just the function itself. So first we differentiate, and then multiply and differentiate. So in order to differentiate p function with respect to x in this case, then firstly what we do is that leave this and make a differentiation gx, and then leave g alone and then make a differentiation of the 1 minus x squared to the some power. Okay, so that's what we do here. So first, then we make a kind of a common factor 1 minus x squared m over 2 in front of them. So this term, then this is the kind of in order to have this common factor, this is the kind of little bit of change. Okay. Then we multiply with this to dp dx, okay. Then differentiate it, and also we do this kind of differentiate by product function, differentiation for the product function, like this. Okay. Then we have this. So at this point you just stop the video and then do this on your kind of piece of paper, and check this one. Okay, so once you have done this, and then this is the kind of this multiplication part, and all this together you're ending up with this. Now this is just a common 1 minus x squared over this m over 2's power. You multiply both sides and you are left with this. So this is the equation, interim differential equation you are going to solve. So I will repeat that here. Now we are going to use a method with series. So gx is in the form of series, an x to the nth power. Okay? X to the n. Okay. So there are second derivative, first derivative, and just function itself. So first derivative, this is the multiplication. First derivative of this is an n minus 1 x to the n minus 2 power. And then this term has already has x. Okay? And the first derivative is an x to the n minus 1. And this is just a repeat of this function. Okay, but here you multiply with the 1, that's this term, n minus 1 an x to the n minus 2. If you multiply with the x square, you're getting x to the n minus. Okay? And here also you have x to the n with minus. Okay? So that is minus this, okay? And also minus is here, so plus this. And then here you already have x to the n, which is a n. So you collected this one here. Because of there is a minus already, so you kind of switch the position. And then all three have an, an. Okay? nx to the n equals 0. And notice that when n equals 0, this is 0. When n equals 1, this is 0. So it can begin with n equals 2. And now you substitute n with n plus 2. Okay? Then your index goes to from 0 instead of 2. Okay, so, well, it's kind of confusing, but if you use a different symbol, that's fine. But you can, because for the sigma, n is a dummy variable, so you can use anything. Then now what you have is that n, instead of n, you have n plus 2. Instead of n minus 1, you have n plus 1. Instead of n, you have n plus 2. Instead of n minus 2, you have n. So this is the term. And then this is the x to the n power. This is to the x n power. Okay? So you can combine these two. Okay? Yeah, you just one step down. You just make a kind of a little bit clean form here. Then both are in x to the nth power. So what you have here is that this coefficient up to n, an, is the same, are the same. So you can draw a n plus 2 equals to this times an. So this is the recursion formula. Then now you can have your function in the series form. So you have the recursion formula, but if you take a look at this recursion formula by comparing consecutive term when n goes infinity, which is x squared. Yeah. The reason for that is that an plus 2 over an, n is large, goes to infinity, then this is n, this is n, this also is n, n. So n squared over n squared behavior, which is 1. Then you have just x squared, kind of ratio. The ratio is just x squared in this case. So this series will converge when x absolute value x less than 1, but it diverges when x absolute value of x equals 1. So it diverges. So we have to truncate the series up to n prime term. So meaning is that a nth prime, a n prime, there is no a n prime plus 2 term. Okay, so in order to make it, we have to make this 0. That's 0 when the numerator is equal to 0. Numerator equals 0 when nth term and prime term. Okay, so this is the kind of convergence criteria or convergence condition. We just made it converge by truncated series. Okay, so truncation, just likewise we did in Hermite differential equation, truncation yields us discretization of energy or quantization. So it gives us the quantum number. Okay, so we have the quantum number L. We let the quantum number both together. L, n prime, absolute value m. So n prime could be 0, 1, 2, 3, all integer number. If we have that, then our n value runs from minus L, which is the integer, to the plus L, all the integer between them. Okay, So this L is the angular momentum quantum number. This M is the magnetic momentum quantum number. Okay, so we have determined beta now, which is L plus 1, because beta equals L plus 1. N prime plus M, absolute value is L, see here? So beta is L plus 1. So you determine beta, and you remember that the energy was h bar square beta over 2i. Okay? Because you have beta defined in terms of 2i over h bar square. So your energy is h bar square over 2i L plus 1. And then your energy is depends on the quantum number L. We index it EL. So EL, L's state in this case, the state which has the quantum number L, the energy of it is EL equals h bar square over 2i L plus 1. Now we go back to assemble theta in this way. Theta was P of X. Okay, at this time we just replace the theta with X. X is cosine theta. Okay? Then we did this to make it regular function. So 1 minus x squared to the absolute m over 2 power gx, and we now obtain the gx in terms of the an series, and x was the cosine theta. So put these two back into each position. Theta of theta equals sine, because this is 1 minus cosine square theta is sine square theta. So sine m's power theta g of cosine theta, then which is an cosine n theta. Okay, so this is our solution. Okay, now the solution to the Schrodinger equation was y theta and phi, which is theta function, phi function, and your phi function was 1 over square root 2 pi and I am phi. Okay, so e to the I am phi, e to I am phi, and function of cosine theta g, and sine, I'm sorry, there is theta. Okay, a sine m theta, and this is the normalization constant. Your energy was here, is this. Then we have L equal 1 from 0, 1, 2, then m goes from 0, yeah, that's 0, that's it, and n prime is 1, is 0 in this case. Okay, L equal 1, m goes to 0 to 1, L equal 2, m goes 0, 1, 2, then n is 1 and 2, 1 and 0, actually n plus m is 1 in this case, n plus m is L. That's how you obtain this n prime. So with this n prime number, with these numbers, and you obtain, you can assemble this Lm relation to this spherical harmonic. Okay, spherical harmonic so has two indices, L lower index for the L, upper index for m. Okay, so L00. Y00, Y10, Y11, Y20, Y21, Y22. Those things from, you make that from here through here. Okay, so you make a tabulation of this. But what we have done actually is we just solve associated Legendre differential equation. So then this corresponds to associated Legendre polynomial. So this is a kind of a sum up or way we make a tabulation of the spherical harmonics, and this normalization constant is here from this function or this integration. The range is x is what? X is a cosine theta. So So the range of it is theta goes from 0 to pi, which is -1 to 1. Then this is a kind of a normalization. Then, well, theta goes 0 to pi in this case. Then this is it. Okay? So this is well, n and l must be the same in order to have this number, but that number is what? Normalization constant square. So we have a square root of it for the normalization constant. So y lm is normalization constant times the, actually this is the associated Legendre polynomial in cosine theta, then phi part. So spherical harmonic is given in this way. Just to repeat this line here. So this is 0, 0 in theta and phi form 1, 0, 1, 1, 1, minus 1, because m value could be minus l through l, including all integers in between. Okay, so this, and then when l equals 2, you have minus 2, m equal minus 2, minus 1, 0, 1, 2. So that's the way we have the spherical harmonics defined. So this is a solution for the rigid rotor, and this also will be used to obtain the solution for the Schrodinger equation of the hydrogen-like atom. So this is the theta and phi part of the solution, the hydrogen atom. Okay, so one application we are going to look is rotational spectroscopy. Basically, we just know the energy levels of the rigid rotor. We can easily look at, we understand what's going on. So energy is given here. J is the rotational quantum number. So which is h bar, the energy is h bar square over 2i, moment of inertia, j plus 1. J is 0, 1, 2. Okay. And also there is the degeneracy. Degeneracy means that different state with the same energy. That's the definition. The degeneracy Gj, the jth level, is that 2j plus 1. Okay? But this will affect the intensity of the rotational spectral lines. Okay, and also the rotational spectroscopy mandate that, or kind of guide that, there is a selection rule, which is you can change the rotational quantum number only by 1. So delta J can be just a plus minus 1. So you can compute the energy difference between the transition, which is delta J plus 1 in this case. So from J to J plus 1 level, J's level to J plus 1th level. So energy of EJ plus 1 is h bar square over 2i, J plus 1, J plus 2. Okay? Actually, this is J plus 1. And for EJ, which is minus this times J plus 1. This is the regular form. So we do this mathematics, then what we have here is this. Okay? And then we put back, instead of h bar, h over 2 pi. Then what you have here is h square over 4 pi square I, and j plus 1. Okay. All right. So this is the relationship for the frequency to the energy. So this energy is equal to h nu. So nu is h, because there is only h, already h here. Nu is h over 4 pi square I, j plus 1. Right. But people define this as 2b for some reason. Okay? So that's 2b. Then b is the rotational constant. But sometimes people just say 2b is the rotational. Sometimes it's confusing. But b is the rotational constant, which is half of this. So h over 8 pi square I is the rotational constant b. So 2b, j plus 1. if you want to do it, well, sometimes you've been required so, and nu twiddle. Nu twiddle is the transition in wave number. So energy in wave number, then you are going to get B twiddle. That rotational constant, also this is called the rotational constant, but the unit is different. Then what you need to do is to divide with c, which is the speed of light, which is h over 8 pi square ci. So both are called rotational constant. What you notice here is that all transitions are actually from 0 to 1 is 2 pi, because 2b, well, this is in rotational in wave number. Then wave number increases into the right hand side, yeah, and this is 2b twiddle. But here, if you if you go from j equal 1, j plus 1 is 2, actually twice of 2b, which is 4b, and 6b, 8b. So in your spectrum itself, it appears in 2b position, 4b position, 6b position, 8b position. So your spectra look like just a regularly spaced spectral lines. That's the rotational spectrum. So we'll solve another one little problem, and then that will at the end of this lecture. So this is an example of microwave spectroscopy of H35Cl, hydrogen chloride. So the spectral lines equally spaced. So equally spaced, separated by this, which means that this is what? 2b, 2b twiddle in this case. Okay, so that's 2b, which is h bar r, which is given in Hertz. So that's 2b, not the twiddle. So 2b is, you remember that, h over what? 4 pi square I, and that's the Hertz. Okay, and I is the reduced, I is the moment of inertia. Yeah? So moment of inertia is obtained, h over 4 pi square 2b. So h over 8, this is h over 4 pi square, and this is 2b. And then this is what you have for the moment of inertia. And moment of inertia is reduced mass times r square. So u is the reduced mass, given that h and cl in AMU, then convert that AM to kilogram. You have that kilogram. And then your R value is that this divided by this reduced mass and square root. And that is 1.28 times 10 to the negative 10th power meter, which is actually angstrom, this part. So 1.28 angstrom, which is in picometer, 128 picometer. So we just solved the Schrödinger equation for the rigid rotor, which will be the part of the hydrogen-like atom, Schrödinger equation. And then the solution is the spherical harmonic, and that can explain the rotational spectroscopy. Basically, this is the material we covered today.